So thank you very much for the invitation to be here. Let me just say that, okay, I always like coming to Oxford. Oxford's very beautiful. So I went back and forth, what I should present in these two talks. And a bit in coordination with Andre, I sort of settled on talks that go like this. So talk number one is more about giving some ideas and a little bit less focused on computations and derivations. And talk two will be more about tools for computing correlation functions. And I'll show you how that works on a board and how to do some kind of, 1/n expansions and so on. But there was a big kind of like confounder in preparing these presentations. Namely, I really am not 100% sure what people's like average background is. Like, I think the union of people's interests is probably everything, and the intersection of the backgrounds is nothing. And so it makes it like kind of hard to actually give this talk. Okay, so there are people like Jim and Zohar in the audience who like know 97.31% of everything I might say. So for them, I want to speed up, but then there are others for which I don't know. Okay, so I sort of decided to be self-contained, but a little bit kind of fast at the beginning. But feel free to just like slow me down or speed me up. It's not a catastrophe if I don't get to the end. You can always ask me more questions offline. Okay, so let me start with a definition, just because I'm a mathematical physicist with an emphasis on the math, at least in my training, so I got to start with the definition. So I'm going to try to present a set of ideas and tools for using field theory to study neural networks. These tools can be used for studying rather general kinds of neural networks. I'm working on that kind of thing now, but I'm going to focus on the simplest kind of neural network, what are called fully connected neural networks. Okay, so just out of curiosity, like how many people know everything about fully connected networks and everything? And okay, so well, you can come give the lectures, that with me. Okay, so this is at least an excuse to introduce the notation. Okay, so all neural networks are parameterized families of functions, but fully connected networks are parameterized families of functions that look like this. So my notation is they take in n zero-dimensional input vectors, which are indexed by these Greek subscripts like alpha, and they give out, these slightly ridiculous looking things, which I call ZL+1 alpha. So these are an R and L+1. Okay, so the n0 is the input dimension, R subcapital, so NL+1 is the output dimension, and capital L is about to be my hidden layer. So here's the way you go from the input to the output. So the way you generate the representation in layer L+1 corresponding to input X alpha is like this. They're basically just two cases. So you apply a matrix of weights, WL+1, applied to sigma of ZL alpha. That's kind of the generic recursion when L is greater or equal to 1. So here sigma is called the nonlinearity or activation function. When you apply it to a vector, these Z's are vectors, just apply it to each component. Okay, and then I'm going to slightly change my normalization in a moment. Oops, there's no sigma here. There's just an X alpha when L equals 0. Okay, so all you do is you start with the input, you apply a matrix of weights, then you apply the nonlinearity sigma to every component, you apply a matrix of weights, you keep going, you do this capital L times L for number of layers, and then you declare yourself too exhausted to continue, and that's the output. So indeed, I turn off the biases. Everything I say can be done with biases, but there's not enough room on the board. Okay, the board is too small. Indeed, there's going to be enough indices and things to keep track of. Okay, so I'm going to preemptively add some normalizations here. I'm going to normalize by the square root of the dimension of the previous layer. It's going to make my life kind of easier in keeping track. It's just a convention for the moment.
I'm sorry, actually, like when the sigma takes value in what?
So I should say, let me write, these matrices WL, my normalization is their NL by NL minus 1. And what that means is that these ZL alphas are NL dimensional vectors. Okay, so when you apply a fixed function sigma, it's a function of one real variable. It just means apply it to each component of the vector.
Oh, okay, so it remains a vector that you're
That's right.
Okay,
that's right. So this is the typical thing. Okay, this is what a fully connected network is. Okay, so what I want to try to convey to you is that at least sometimes when people talk to me about neural networks, they talk as if nobody will ever understand anything about deep learning. Neural networks are too complicated. Okay, those people are basically crackpots in my view of things. Actually, neural networks are so simple that I think we'll basically eventually understand many interesting things and already understand many interesting things about their analysis, as long as you're kind of honest with yourself about what theory can possibly do for you. After all, theoretical physicists are not the best at building jet engines. You need a wind tunnel. And you have to be clear about what you hope theory can accomplish, right? Okay, but before I tell you the kinds of questions that you can answer using in particular techniques from statistical physics, and sort of other related areas, I need to tell you, and this is the kind of thing where I don't know how well people know, how neural networks are actually used in practice. Because the things we hope to answer are related to their practical use rather than other questions that we might make up, at least in my kind of rendition. Okay, so here's my definition, and I want to give you a kind of cartoon for typical use of a neural network. It's going to be relatively short, but hopefully not too painful. So just out of curiosity, how many people have trained a neural network? Okay, basically everybody. So I can go relatively quickly, but I'm still going to draw my pictures, and you can yell at me for how bad the pictures are as we go along. Okay, so in my view, yeah, please.
I can yell to increase the font.
Can people not read it? Okay, I'm gonna try. How about this? Well, okay, the font will get bigger over time. It's like in the diffusion model. We're gonna increase the variance. Okay, I'm not sure where. Okay, good. So for me, at least, the typical use of a neural network has a couple of stages. I'll try to write bigger. So step one is you go and you observe some training data. For me, these are just some X alpha, f of X alpha pairs. Okay, alpha goes from 1 up to little n. This is just an excuse for me to introduce my various notations. So capital N's are the widths of the layers, and little n is the number of samples. And okay, some of my statistical physics colleagues like to put p for the number of samples, but I've disabused myself of that. Okay, little n it is. Okay, and so what's the goal? The goal is to try to approximate this unknown function f using only samples from input and either the exact value of f or some approximation to it. Okay, so how do we do that? Well, we do that by fixing a model. So in our case, we fix some particular neural network architecture. So you fix the depth and the nonlinearity and the hidden layer widths. So the input dimension and 0 in the output dimension are fixed for you. So you can only fix the n1 up to n capital L. And what does this really mean? Okay, I'm going to draw a slightly ridiculous picture, but here I go. So I think this everyone on Zoom can hopefully see, though they may wish they had unseen it. Okay, so this really means two things. This means there's a space which is R number of parameters. And so the parameters here, I call them generically theta, but they're literally just the entries of these weight matrices, right? And this is the space of functions you can compute, or some parameterization of it. When you fix the matrices, you get some particular map from inputs to outputs. And this is a representation of the space of functions you can compute with your neural network that only a computer could love, right? The trouble is, if I give you a neural network and I simply give you the list of all the parameters in the model, that tells you absolutely nothing. It's a little bit like if I told you all the positions and momentums of like the particles of air in this room, that tells you literally nothing other than I'm a monster and I gave you a huge kind of list of numbers, right? So really we want to think about it like humans. And so here come my drawing skills. So here we are. So roughly speaking, the way I think about it, and I think most humans, is for every parameter vector theta, you have an entire function, which I'll write here, ZL plus 1 of theta. And so if you fix theta, you get some mapping from inputs to outputs. And what you hope is that either the function f or some good approximation to f lies in the space of functions you can compute. Okay, so I draw it in this funny manifold-like way because the map from parameters to outputs is very nonlinear. Okay, so you might move the parameters a little bit here and you might get some complicated movement in the space of functions, but this is something that you and I can love and talk about. This is something like, well, on these kind of inputs, you get these kind of outputs, right? That's the language that we use. Okay, very good. So I'm an optimist by my nature. And maybe you can tell I'm like a happy-go-lucky person. And so I think that the function f is in the space of functions computable by my neural network. In fact, my mental model is neural networks are so big, they compute every function possible. So I think of this whole cartoon as kind of being silly, but it doesn't matter, I like cartoons. Okay, but how do we find this function f? Well, we do it in a priori a pretty silly way. We say we have no idea what setting of parameters gets us close to function f. So we choose the setting of parameters at random. So this is usually called initialization. And you kind of throw up your hands and you say, choose theta at random. Okay, and for us, I'm just always going to do Gaussian random, although it doesn't have to be. So this is going to be my notation for the variance of the Gaussian distribution in every layer. So all my weights, all the entries of all these weight matrices are going to be Gaussian random. Okay, so everyone is either jumping up and down or maybe heading for the hills because it's like, oh my God, random matrix theory is about to appear. You have big random matrices. So it depends on your penchant for such things. I like random matrix theory. So here we go. So okay, I'm going to continue my cartoon, right? This probability distribution is a very simple-minded distribution over in the space of parameters. It's just a independent Gaussian in every coordinate. So it kind of looks like that if I were to draw its like density plot. But because the map from parameters to functions is very complicated, actually the initial probability distribution is rather complicated over here. And this is, so I wasn't here unfortunately for Jim's first talk yesterday, but if I channel my inner Jim, we're going to get some kind of like complicated interacting field theory. We're going to try to describe it in a moment over here, but like, you know, that's the point of the cartoon. Okay, you sample some theta 0 from this distribution. This gives you some starting point, some starting function kind of over here of theta 0. And you say, great, I have a starting point for my optimization. But of course, this place where you start your optimization has nothing to do with the function f you are trying to fit. And if it does, you should immediately go buy a lottery ticket because you're the luckiest person alive, right? We have to somehow use the data to improve our initial guess for theta. So that's kind of the fourth step of the typical use case. Okay, so then you optimize. And optimization is always done by some variant of a first order method. So I'll just write the most generic one. So you iteratively improve your guess for the parameters by moving in the direction of the negative gradient of some loss function L. And okay, L can take many forms in practice, but as an example, just take it to be the mean squared error over the training data. That's a perfectly fine thing to do. Alpha minus y. I guess I usually write here f of x squared. Okay, so I'm just trying to give you some kind of cartoon because it's going to be relevant to the questions I'd like to answer. Okay, so what happens? Well, it's hard to prove theorems and easy to draw pictures. There's some evolution in the space of parameters, and then you get some evolution in the space of functions, and maybe it kind of looks like this. Okay, I'm an optimist, so I think you're going to get to the function now, please.
I think I'm missing something basic. Can you explain the little L superscript again? Because I'm a little.
So little L is the layers of the network, as they're called. So every time you go from the representation in layer little L to the representation in layer little L plus 1, what you do is you apply your nonlinearity, and then you hit it with a weight matrix. That's just the definition. And maybe I should say little L, just to be explicit, runs from 1 up to capital L in this kind of picture. Okay, if you really want, from 0 up to L plus 1. So it's like the way you compute the output from the input. You process it through a sequence of layers, and that's a little L.
I see. So you only use capital L plus 1 because that's the kind of thing you want to get.
Yeah, correct. So capital L for number of layers, script L for the loss. Okay, there are many N's. I apologize, but not really. That life is tough. Yeah, but it's a fair question. You should keep asking me questions like that. Okay. Okay, great. So at least to a first order approximation, this is really how people train neural networks. That's basically the set of steps. Of course, it's not, and I'm a liar, and so on, because all these steps are kind of hard. All my colleagues in practice, people who have to simulate from complicated lattice field theories, will tell you don't just get data. Like, you know, you have to roll up your sleeves and do something sensible. But okay, I don't worry about it too much. I call it script D, and I move on. I don't know what the big process. Okay, so the question I think at a high level is, can we make sense as people who know something about techniques for studying large systems that are undergoing some interesting dynamics of what this learning procedure is? Roughly speaking, I want to understand where I start my optimization, and I want to understand something about the trajectory of the optimization and say it in human computable terms. Okay, this is like a description that a computer can understand. because it's very algorithmic, but it's not very transparent conceptually. Okay, so let me just pause for 1,000th of a second to see if people have questions or comments about this. This is like my attempt to introduce some notation. My plan next is I want, just by way of introduction, I was told to make this accessible to people who don't know ML so well, to like maybe sketch a couple of the very big high level questions that I think are really interesting. Then I'm going to tell you exactly what I'm going to focus on in these 2 lectures, namely computing correlation functions at initialization and also using them for doing things like Bayesian inference and so on, as I'll explain. And you know, I'll get into what I want to say. So but is this okay for people? You know, my notation could be like confounding for all of what I want to say. Okay, people seem at least moderately happy, which is okay, saying a lot. Right? Great. So let me just very briefly sketch, okay, some of the big questions from my perspective that one tries to answer when studying deep learning theory. This is not meant to be an exhaustive list, and I think like there's an interesting debate to have about which questions are already solved and in what sense and so on. So don't hate me too much, but I'm just gonna write them down. Okay, so question number 1 has to do with the seemingly insane, at least maybe 20 years ago, seemingly insane notion that, look, the number of parameters in practice is easily millions, billions, sometimes trillions of parameters. So you're basically optimizing by a greedy local search, like a gradient descent method, a function of like 17 trillion parameters. So I was always taught growing up, that's a big no-no. You're not allowed to do optimization of these complicated non-convex functions in high dimensions. Think of spin glasses. And so the question is, which minima of the loss do we find by gradient descent? So implicit in this question is basically this kind of cartoon. Okay, this is again what I was sort of taught. Here's the theta space, and okay, you might be worried, what if this is the function L? You know, that's what I was always drawn back in the day. Well, it sounds like a disaster. You know, you initialize, you're going to find some local minimum, but how do you find a global minimum? It's going to take you exponential time to try to find it, and this is a disaster. And okay, so there's a lot of hand-wringing about this, but I'm here to tell you, don't worry about this. This never happens. Okay, that's not a thing. If you ever trained a neural network, you never had the problem unless you implemented it incorrectly. You didn't fit the training data. You always get a global minimum of the loss. And fundamentally, it's something like, this is a bad picture for the loss landscape. It's more like, it's very easy to fit the data because you have so many parameters. That's the maybe right thing to think. So let me try to draw a kind of ridiculous picture, and you can laugh at me or not. So I think of the space of minima as basically looking like this. It just looks like the function is non-convex, but there's infinitely many minima. There are these huge positive dimensional manifolds of minima. And anywhere you start, this is meant to be a graph of the function, you just go downhill. It's kind of like the loss function is like a canyon, and all you have to do is get down to the bottom of the canyon. So that's why I phrased the question this way. It's not so much, do you find a global minimum of L? The answer is basically yes, always in practice. But the question is, in fact, which minimum do you find? Some minima, so all these minima will fit the data the same, but some of them will do well when you test on new data points and others won't. And so that's kind of like I think a central question people are still struggling with in a sense. A lot of progress has been made. Okay, I'll say something about that maybe as we go on. Okay, so that's kind of big question number 1, something about the success of optimization in high dimension. Okay, so question number 2 is,
What is going on? Central to that is the idea that over parameterization is your friend.
Yes, precisely. Yeah, indeed. Somehow, when you're over parameterized, you expect it to be easy to fit the data. And now, what counts as over parameterized is a little complicated, because normally people say something like over parameterized means more parameters than data points. But if I repeat the same data point a million times, I haven't increased the number of data points. So the question is like, what's the effective number of data points? Right. You know, what's the effective number of degrees of freedom that, so okay, there are some subtleties there, but roughly that's kind of the.
One thing you hear people say, more sort of Twitter effect or extra Twitter, you know, that, well, you're in higher dimensions, there's always a way down. But that we know is not true for spin classes, the classes, and so on. So it has to be this particular class of loss functionals
That's right. There's still interesting open questions that say things like, what are really the properties of the loss functions that we're minimizing in practice? There's things like NTK analysis, which sometimes we'll say the loss actually does look convex, so it is easy to optimize. But optimization works even for non-convex settings, and so there's just some like big set of things, and I won't say much about it unless you guys force me to. Again, and then it'll be a ramble, which is maybe okay. Okay, so that's kind of question number one. So question number two is, what can we say about feature learning? Okay, this is I think a very interesting set of questions. But okay, so in fact, if you go to a practitioner, I think, and you ask them, well, what's so great about neural networks? One of the things people will say is that they're great at learning features from data, features that you can reuse for downstream tasks. That's kind of what foundation models do, and so on. But what they won't often say is they won't maybe be totally precise about what they mean by features and all of this. So let me just make one kind of concrete comment about this. Because I'm going to come back to it in the second lecture. I'll state the theorem about it, which I think is kind of like something that I was looking for a while. So one kind of silly thing to realize is the following. Well, not too silly, but a little silly. Okay, so here I get to introduce more notation for everyone's joy. So this for me is the odd component of the output from input X alpha. Okay, there won't be too much more notation, but I'm sorry, I just need all of it. Okay, so just by definition, if you write out what I have on the first kind of board, it looks like this. You sum over everything in the final hidden layer, all the neurons, and you have these weights W, L, I, J, and you have sigma of Z, L, J, alpha. Okay, that's literally the formula for the output of the neural network. I know everyone here knows how to multiply a matrix by a vector, but I want to make a point about it. So all of traditional machine learning, or a lot of traditional machine learning, has to do with what are called linear models. Okay, when people say you have a data set and you fit a linear model to it, what they mean is I have a model that's linear in my parameters. That's what they mean. And so a linear model, something that's linear in the parameters, always looks like this. There's just some collection of basis functions, psi j of x alpha, sort of just make explicit the x alpha over here. And these are given to you. And what you do is you fit the coefficients in a linear combination for this particular collection of basis functions. That's how you make predictions. And that's what people mean by linear models. And linear models don't learn features. These psi j functions in the machine learning world are called features. And so what you can think of a neural network as doing is the following. You see, these basis functions, when I write the output of a neural network as a linear combination of some parameters against these sigmas, these basis functions themselves are learnable, right? The previous weights in the network actually parameterize these basis functions. So at least one version of feature learning is basically saying these are learned, like data dependent basis functions or feature functions, if you want to say it this way. Okay, so when you're actually training a neural network, I think a good thing to have in mind is you're simultaneously learning the coefficients in a linear combination and the functions whose linear combination you're taking. So that's one concrete way you're doing feature learning. Yeah.
This is what's sometimes called latent. Like you in the literature, they often refer to like finding a latent space.
So the short answer is you could call it that, though typically that's not the word people would use. So typically when people think of there being a latent space, it's more like you have a model that goes from some high dimensional space and you force it to have a bottleneck, which is low dimensional, which you hope describes your data, and then you have some decoder from that kind of low dimensional space. So it's not unrelated, but I think that's maybe like too specific of a terminology to use. Yeah. Okay, but just to kind of be precise, like from my point of view, every set of basis functions determines a Hilbert space. Okay, as mathematical physicists, everyone loves Hilbert spaces. And you might say that instead of working in a fixed Hilbert space and just doing linear regression in the Hilbert space, you are learning a Hilbert space and learning the coefficients in the Hilbert space. And so you can start to ask things like, how does the data impact the Hilbert space you learned? Okay, there's like lots of precise questions to be asked, most of which are unanswered. Okay, that's why I bring them up to
I
you.
realize that I haven't followed this carefully enough. So can we just slowly go over this again? So the alpha was a subscript for which I had a vector that was just a component of the vector. And I is what again?
Yeah, so right, so alpha indexes the whole vector of inputs. So X alpha is some cat
Some
index.
particular one.
Yeah. And then the I is a neural index. It's like the component of a vector somewhere. And this thing is the layer in which you're studying.
Okay, and then on the right-hand side, I have,
So on the right hand side, these are the weights in the final layer that go.
so just from the penultimate layer to the ultimate. Layer.
Yeah, precisely. And then these are the components of the vector that you're kind of summing up, that you've gotten up to that layer.
So I guess what I'm confused is when you said that's learned, I thought that was a fixed.
Sorry, what I'm saying in neural networks, to compute the ZLJ alpha, that involves all the weight matrices, all the W's up to the final layer. So and when you do this kind of optimization, you optimize all of them at the same time.
Next thing you're doing is everything that.
Precisely. So if you weren't training all the previous W's, you would simply have a linear model over these particular set of fixed features. But I'm saying you're learning both. That's quite literally what's going on. It's not the only reasonable way to make sense of feature learning for what it's worth, but I think it's a sensible way that's kind of implicit and common in the way people talk about it. And it's also a common thing people do. They'll train a big neural network on a data set, and then they'll basically just keep the psi j's that they learned, and they will retrain the w's on some other data set. And so they just use it as a feature extractor. That's not an uncommon procedure for fine tuning, as it's called.
So I think the feature is whatever happened up to that point, and then with the freedom to change.
Precisely. Yeah.
Yes, so presumably if you're guessing, well, if you're aiming for functions with rotational symmetry, you discover your spherical harmonics, right?
Well, so right. So it's a good question. So this very quickly gets to unanswered type questions, and you're basically saying, suppose I make some structural assumptions on the distribution that generated my data. Well, then what can you say about the statistics of the C's that you learn after training? Like, what do they encode about the data? Do they know about rotational symmetry of the data? Do they know about other things? And the answer is pretty hard to answer. So maybe, I would say maybe.
So I'll put that question another way. If you're doing dog pictures, you would have ears.
Yeah. And there is such a thing. So it used to be really popular and then people stopped because they realized they could always do it. You take a big trained network, and after training, you fix a neuron in the network. Let's say one of these final C's. You fixate on some particular one you learn. And what you do is you find the input that actually maximizes the value that you get. And what you find are things like ear neurons or whisker neurons, where there's these masses of things that look like ears or whiskers, so they call it feature visualization usually. So that's a thing. But again, explaining that is, yeah. But it's a good question. Okay, so I think this is like an interesting set of questions. Okay, can I say one final one before finally getting to my talk? I'm going slower than I thought, but that's okay. That's good in sense. Okay, so maybe just as context for me, I came from very theoretical math physics, so I was always studying scaling limits of neural networks. That's where I'm getting to in a moment. I think of this as having lots of large parameters, number of data points, the widths of the layers, the number of layers. I just want to take everything to infinity and see what happens. That's kind of the theoretician in me talking. But there's a horribly and beautifully practical side to all of this, which I want to briefly point at. And so I'll call this describing scaling limits or degenerations of your theory, or on the practical side, doing what's called hyperparameter transfer. When you scale a model. Okay, so the basic kind of question is like this. In order to actually do this training successfully of a neural network, you have to make a bunch of choices. You have to do things like choose how you're going to initialize different parts of the network. You have to choose things like the learning rate you're going to use. If you know what batch sizes are, you have to choose the batch size. There's also momentum coefficients and weight decay, and there's all kinds of what are called hyperparameters, things that you don't optimize by gradient descent. You don't optimize the learning rate, you have to input that. If you don't make these choices well, your model won't work well. That's kind of a fact of life. And so the question is, how do you actually kind of make these choices in a principled way? So let me write something sensible, which I have prepared here. Okay, so here's kind of the question that I think of for myself. So how to scale things like the initialization scheme. So how do you scale the kind of variance of the weights? The optimization hyperparameters. So these are these things I alluded to, things like the learning rate, or more generally the learning rate schedule and the weight decay and the batch size and all of this. So with growing model size, okay, data set size, compute budget, and so on, to get consistent limiting theory. Okay, so this on the one hand sounds like a theory question. Basically, should you scale all the things in your problem so that you have a non-trivial limiting dynamics by which your network is learning? But the flip side, which is 1 second, is like purely practical. Rather than someone coming to you with a big neural network and making it infinite size so you can study it as a theorist, someone comes to you with a big neural network and you want to make it much smaller. And then you guarantee them that the small network resembles the big network in its training dynamics, and you optimize the hyperparameters. And you try to figure out how you set your learning rates and so on. Okay, so yeah, so there was a question.
I'm just curious how scaling up theoretical work then compares with what's being done in meta learning, where you do learn all of these things with gradient descent by just chucking it all into another neural network. There was a talk at ICLR doing this.
Yeah, indeed. So what I would say is this. About 90% of what people do is not public. And so it's hard to give an honest answer to that question. But, okay, I was hoping I'd actually have this done before I came here, but it's not quite done yet. I've been working last year, 18 months with a applied group at a company called Cerebras, which is a hardware company. They're kind of like an NVIDIA competitor. And so we're working on taking like basically field theory principles for scaling models and like actually testing them in like the biggest, baddest LLMs. And we do significantly better than they were able to do using everything they could possibly tried before.
Including UP.
Yeah, including everything. So we outperform everything because all of it misses some aspect of the correct scalings, it turns out. And so like at least that's like my one data point for a team whose job it is to get the best possible performance at large scale in practice, and we're very good at what they do. The theory can actually buy you like a significant amount, enough that like they gave us plus infinity compute budget to run the experiments, more or less. You know, so like that's like the most honest answer. So I flag that as like I think a genuine question that's very interesting, and this is like one of the best places if you want to take theory and make it useful in practice is these questions of model scaling. I'm actually working with some people who do data analysis at CERN, for example, to scale up the kind of graph neural networks that they use in their pipeline. Because it's not 100% clear actually how to do this for kind of equivariant networks. Doesn't matter. That's not really what I'm talking about. Okay, so let me now finally state the goal for these 2 lectures. I tried to kind of give an introduction. My hope is that this is helpful for people who are coming from like the I study neural networks all day long, every day kind of place. And then like I'm going to try to make it useful for people who study field theory and maybe know a lot about neural networks already too. So here's sort of my goal. I'm going to be precise about the goal, and I'll tell you why I care about it. So I want to kind of describe some specific field theory-ish techniques for the following kind of problem. So my goal is going to be to compute correlation functions, because what else is there in life? Correlation functions. Okay, of the following objects. So I'm going to be interested in the various layers of the neural network, the representations that I get. I'm going to be interested in the gradients of those representations, both with respect to parameters and inputs. I'm going to be interested in second derivatives. Okay, I'm going to be interested in basically like all the statistics of these things. And in the following regime, so I'm going to be most interested in it when the hidden layer widths, the depth, the number of samples are all going to infinity, or at least some of them are going to infinity. So I'm interested in asymptotic questions about neural networks. Okay, and at least in these 2 lectures, I'm going to focus primarily on what happens at initialization for reasons I'll explain in a moment, and when you have W Lij, I'm gonna rewrite what I had over there, are just independent Gaussians with some variance. Okay, so this is like a precise statement of my goal. And now you might say, wait a minute. You told me all about learning things with neural networks, but you're not gonna study learning? And I say, hold on, let me erase the board. Okay. So let me tell you why I want to study this particular set of questions before you yell at me too much. So I'm gonna erase some of this.
You can do it now, or you can do it now.
You slide it, you can push it upwards.
But then I'm gonna lose things.
You can get it back if you just keep going.
Andre, just show him. Andre, show him.
No, I think I understand, but then what am I supposed to, because I don't want to lose the. No, but I want to be able to point to it and not have to move. I think it's okay. I think this is the Pareto optimal move. So we can take a second anyway. Okay, so okay, let me give you a couple of motivations for why I'm going to try to analyze this and why actually you learn quite a bit about learning by doing this. Okay, so motivations. Okay, so motivation number one, I think is kind of obvious, at least to me, or at least, okay, it's what I literally just erased. This is quite literally the study of neural networks at initialization, right? So for me, somehow, like, if people were to tell me, oh, why do you study random matrices? There's no structure in random matrices. I tell them they're a crackpot, with hindsight, right? There's a lot of interesting things about random matrices. They come up all the time. So in particular, as I will try to emphasize, studying neural networks at initialization, at the very least, tells you things about basically what are the thermodynamic variables. Thermodynamic variables, or maybe put a different way, what are like the order parameters to track when you actually study not only initialization, but training as well. Yeah, I'm going to explain that in a second. But like, to me, it wasn't totally obvious. I have, and I'll go into this in a second, I have these widths of the layers, I have the number of layers, I have the number of samples. Like, what am I supposed to do when they all go to infinity? It's kind of like a well-known thing in general that none of these limits are going to commute when they grow. And so like, what possibly pops up? Okay, so I'll say something about that. Okay, so thing number two is just because you're studying things with random weights doesn't mean you can't say things about training. So you can study the dynamics of training near initialization. Right, so for example, if I wanted to know what my neural networks learn from one step of training, right? What does the first gradient update do? That's just a question about initialization. That's just a question about gradients at initialization. If I wanted to know what two steps of learning do, that's just a question about second derivatives at initialization. I'm just saying you can Taylor expand. Taylor expansion is your friend. And so if you want to understand, especially early training dynamics, you're really just studying neural networks at initialization. Okay, and somehow here there's an important principle that comes up, okay, both for understanding training dynamics and for kind of like this question number 3 of scaling limits. What you can basically ask, so it's like a kind of, I would say, big idea or kind of useful idea, let me not call it big idea. You basically ask that various order parameters, and I'll explain in a moment which ones I have in mind, at initialization are order 1, and the updates to the order parameters are order 1. Okay, so you have some kind of well-defined dynamics, regardless of how big your model is, how many data points you have, and so on. And this gives some principles for choosing things like how to scale your learning rate or your batch size or whatever you want as you scale up the model size. And these principles turn out to be principles that if you work harder, you can upgrade to describing all the training dynamics of a neural network. It's not only at initialization anymore. But B, like super useful in practice. They actually give the kind of right procedures for doing model scaling in every case that I know. Okay, so I will say something about that, but let me leave it at that for a moment. But let me give you 2 more kind of interpretations of why study neural networks with random weights. Okay, so We should all feel lucky that Zohar is here, and any question you have about Bayesian inference with neural networks, as long as the depth doesn't go to infinity, maybe you should ask Zohar, right? No, but it's like, so let me state it, and then I'll say it in a more serious way. So you can start to ask questions about the statistical mechanics, or if you want, the Bayesian inference with neural networks. What I mean is, just because you're studying things with IID random weights doesn't mean you're not asking complicated questions about the distribution with random weights. So in particular, the Gibbs measures you get from neural networks. So let me kind of write down something that I hope will be reasonable for people, but you should yell at me if it's not. Okay, so I have some input X. So I have some neural network. Rather than training it by gradient descent, I'm going to train it by Bayesian inference. I think of this probability distribution as my prior. I observe my data, I have some likelihood, and I form the Gibbs measure, and this is going to be the partition function for the posterior. So let me just write it out, and then if people have questions, you should just ask me, but maybe this crowd won't have questions. So it's the ensemble average over initialization of this thing. So I put in a source term, e to the minus I tau C L plus 1 alpha naught. This is the thing I'm interested in. I'm interested in the statistics of the posterior evaluated at this particular input. And then I do minus beta over n sum on alpha goes from 1 up to n of, okay, whatever, the training loss that I had from x alpha squared. Okay. So my point is this. If you just take the initial distribution, that's your prior, that's how statisticians would talk about it, and you tilt it by e to the minus beta likelihood, okay, you get the Gibbs measure for the neural network, which the statisticians call the posterior, and this is the generating function or the characteristic function for all the moments of the posterior distribution. So I'm saying if you know your initialization distribution really well, you can compute also what happens after learning, but the learning that you have in mind here is not by SGD. If you want, formally speaking, is by Langevin dynamics and taking time to infinity and so on.
Yep, can I ask about point number 2, how generally you think it is? For instance, let's take a system that grows.
Yes.
It has a time scale before which it doesn't do much and suddenly it learns something.
Yes.
It seems kind of miraculous that whatever is happening very early on before it learns something, even in this case, would somehow predict the right parameter scaling. But in practice, it is common practice to tune hyperparameters early on training. And so do you have any?
So okay, so I'm thinking about that quite a bit these days, and I think it's like an excellent question. Here's what I would say. I would say grokking, a lot of grokking is about kind of 2 bottlenecks being removed. Your model has to be big enough in order to learn a kind of representation. And you have to have enough data for the model to pick up from the data the right structure to learn. And I think as long as you have enough data and your model is big enough, then it should be that actually very early on in training, everything is determined by these kinds of rules. It's just from your point of view and my point of view, nothing is happening. And so it's hard to imagine what's going on, but it's something like if you just initialize near the right kind of saddle point and you're going to diffuse around the saddle point, but as long as you have enough data, you can resolve the right directions to escape the saddle point, and those are the directions along which you'll grok. So some kind of very generic kind of description like that. So that's the best explanation I have, because it's really truly puzzling, as you say, if you grok after 10,000 epochs, why is the first step of training telling me anything? And yet it's actually pretty consistent for doing so. So I think it's something like that. It's something like we don't fully understand what's being grokked, but once you're close enough to the infinite size model, basically, and it's hard to know what close enough means in terms of data and model size, then somehow these prescriptions are good enough, because they basically take the hyperparameters of the optimizer, for example, and they make them dimensionless with respect to model and data set size. That's sort of how I think.
Yeah, a related question on 2. So this order 1 business is order 1 in various different parameters that you have in your model, for instance, these things. Can I think of grokking as being related to scaling in the amount of data?
Well, for sure it's related to scaling the amount of data in a way nobody understands.
Just in the sense that as the amount of data goes to infinity, presumably I learn it very quickly. As it goes to 0, I have no.
Oh no, I don't think so actually. I don't think so. I don't think that's what happens. I think it's more there's a minimal amount of data you need in order to grok. And past that, grokking necessarily takes a long time.
I guess if I want to have a prescription for how to grok, can I take something in the training zone and just back off on the amount of data and try to see it that way?
I guess what I'm saying is, I think my, like, from the examples I know, they're mainly the modular kind of arithmetic examples of grokking. Once you're above a certain threshold in the data, all your training curves will look the same. It doesn't, like, the time when you grok won't matter. Of course, if you just show me more data, it'll look like I grok faster. But if you, for example, have a constant batch size, for sure, if I showed all the data at once, it might look like it groks faster. But like, you have to do apples to apples, and then the actual loss curves, like on the validation set, will align. That's what happens in the modular examples, at least. But I don't know more generally. Certainly, I don't have a theorem about it. So like, you know, tomorrow you might show me a counterexample. I'd be happy or interested. Okay, well maybe somebody, yeah.
So what's grok?
Right. So grokking is the grokking is the following phenomenon. So you train a model, and very quickly you fit the training data almost exactly. But on a validation set, like on held out data that you don't show the model, you're doing very poorly. Basically, IID random chance poorly. And then much later in training, you actually perfectly fit the validations. So it's like this kind of time delayed like transfer from the training data to the validation data. And like the colloquial usage is, at that point you've grokked the problem. If you've ever read like Douglas Adams and the Hitchhiker's Guide, I think that's where it comes from. Am I right? People know?
This is like cut off.
Say again?
Like cut off.
Yeah, sorry, yeah, that was a irrelevant comment. Okay. Okay, this is motivation number 3. Yeah, I'm gonna try to get to motivation number 4 before my talk ends. How much time do I have? I have lots. Okay, I'm doing well. Okay, so let me kind of put erase. I'd be systematic. I always get too excited and then I don't erase and then I try to fit it in and then it doesn't go well. Maybe I should have followed Andre's prescription, but now I can't go back. There's no going back.
While you erase more, so the relationship between number 2 and grokking, you're saying, is more of an open question from like some of the other.
100%. I would say everything about grokking is an open question from my point of view.
Very mysterious to me.
Yeah, indeed. So sorry, I just mean this seems to work well in practice.
Yeah.
And like there are some situations where you can prove it's going to work well, but in those situations you have no idea if you're going to grok. So like,
It's not good.
yeah, correct, for sure, that's right. Okay, so number 4 for me. So okay, I erased this picture where Shivaji and I were going back and forth, and I was saying, oh, there's so many different ways to fit the data. The question is which way you learn to fit the data. Well, the basic point I want to say is when there's many ways of fitting the training data, which way you learn depends very much on where you start. Right? Your optimization is some kind of greedy local search. So you start somewhere and you try to go as quickly as you can to the space of ways that fit the data. That's what gradient descent does. And so if you initialize near simple functions, you're likely to find a simple way of fitting the data. Okay, that's like a cartoon. So there's actually a lot of the kind of what people call implicit bias or implicit regularization or inductive bias of neural networks, I think is built into the fact that at initialization, they're surprisingly simple objects. And you don't learn more complicated things than you have to. Okay, that's kind of like something. But let me say, you can study SGD, can study full SGD, and people do it in 2 ways. There's this beautiful DMFT work, pioneered in large part by the group of Genghis Pelvan at Harvard. DMFT means dynamical mean field theory, MF. You know, didn't quite look right. Essentially what they find is that when you identify the right order parameters, you can write down interesting kind of like mean field evolution equations for those order parameters that work for essentially any kind of neural network you want. They work for fully connected networks, they work for residual networks, they work for transformers. You can write them down in any setting you want. It's a very beautiful set of tools. Okay, and then I'd be remiss not to mention my own work. Okay, I'm sort of up here, I don't know, it's kind of awkward, right? So there's the DMFT stuff, and then there's kind of this kind of like, I would say like near NTK, I'll explain later, but think of all the widths as being quite large and the depth not being too big. Basically, there's a limit which I'm about to introduce in just a moment, which says fix the depth, let all the widths go to infinity. Your neural network becomes very simple in this regime. It's called the NTK limit. It just becomes a linear model where the initialization very transparently determines all of training. It's easy to write down analytically the entire training trajectory of a linear model. And so what you can basically do is you can do perturbation theory around the infinite width limit, and you can describe how the decay or how you evolve when you're almost at infinite width, but not quite. Okay, so I'm going to get into that. And let me just flag all of this stuff I'm going to present is based on joint work with Sho Yaida and Dan Roberts. Well, I don't know how they would describe themselves now, but they used to be high energy physicists. Now they work at OpenAI. And so I don't know what they do. Maybe they're still high energy physicists, but it's not completely clear to me. Okay, so I'm going to get to that, but I hope I've motivated at least a little bit the study of random neural networks, even if you're not like a mathematically inclined person. There's plenty of math reasons. Okay, very good. So let me stop for 1 second again and ask if there are questions or comments, because I'd like to now move on to like I gave you some big questions. Here are some motivations, and I want to like tell you 2 stories briefly about the kinds of things I'm going to show you how to derive at least a little bit in the next lecture.
Just a question about this. So if you didn't put mu p up in before, is that sort of because you view it more as like a scaling argument and it's not identifying thermodynamic variables as much, or?
Oh yeah, good question. So the short answer is yeah, like at least from my point of view, mu p doesn't really describe for you the limiting dynamics. It says that like some limit exists. Like it sets things up in such a way that you're going to get order 1 updates.
It sets things up to get to, but it doesn't describe the evolution.
Yeah, precisely. It's kind of like, what's the way of saying it? It's like maybe a reasonable way of saying is it's kind of like it sets up the SD and proves that it doesn't blow up, but it doesn't derive the Fokker-Planck equation somehow.
Yeah. So
that I can sort of see or try to see a bit more clearly. But I think it's totally reasonable to add here things like, okay, mu p, before mu p there was just mean field. You know, like there are a bunch of different kind of like mean field interacting particle approaches. That's how I think about them, just studying the infinite width limit. But this is the only one that I know that is like, it gives you closed form solutions or like closed form equations for the evolution of like the training dynamics.
And as I recall, for instance, from trainers and Blake's notes of your school, they sort of use mu p as like the jump off point for the DMFT detailed evolution analysis.
Yes, precisely. So the mu p basically guessed using such prescriptions how to scale things. And that was like a key like contribution. And then they took that scaling and they did some saddle point, you know, monstrosity or beautiful thing, depending on your point of view. Yeah.
I have another question for you later, but it's not.
Okay, great. Okay, so let me just
Boris,
yeah, please.
It's the same thing I asked you earlier, but you said something since maybe the last time. So the old von Neumann objection was get 5 points and 17th order polynomial and get features which are not really there.
Yes.
You seem to be somehow suggesting that if I pick the right 17th order polynomial at the start, that I'll do a better job.
Definitely. So maybe I can't help myself when I draw a picture.
Sure.
Okay, it doesn't matter. I'm committed to drawing the picture. So let me show you the simplest kind of example of this. So suppose you have way more parameters than data points. So you have R number of parameters. My parameters, I'll call them theta. And I'm just studying a very, very simple problem, just a linear model. So L of theta is the norm of like theta transpose x minus y squared. Okay, so this is a situation in which this is the set of thetas such that theta transpose x equals y. There are just infinitely many ways of solving my system of equations. And you might say, so the von Neumann objection is, look, you can go arbitrarily far. In fact, you can go off to infinity in these directions, and so you can make arbitrarily crazy predictions out of sample. What's going on? Well, what's going on is the following. So a kind of, I think, really beautiful calculation is, I mean, it's very simple, but it's really beautiful. If you take the gradient of the loss, which is what you're using to actually make your steps, what you find is the following. You find that it's x transpose times theta transpose x minus y. And in particular, you find that it's in the column space of X transpose. So the reason that's important is, you know, there's the kernel of X transpose, and there's the column space of X transpose. If you want to say it this way. What this is telling you is that your optimization algorithm actually tells you don't go off to infinity. It says no matter where you start, if that's your theta 0, you're just going to project orthogonal projection. That's where you're going to end up on the space of interpolants. So what I'm saying is, if you initialize in your simple functions, in this case in your 0, and you just run a greedy optimization algorithm, what you'll find is you'll actually always get the minimal norm interval. And so now it's like your algorithm has actually secretly chosen for you a particular way of fitting the data. And indeed, when we fit in infinite dimensional function spaces, it's very common to take something like the minimal norm interpolant of fitting the data, and that can perform very well, even when there's an infinite number of parameters and a finite number of data points.
I'm saying the actual magic is that random initialization of networks that we use ends up being pretty good already.
Well, what I would say is there's two pieces of magic. One, somehow the random initialization doesn't initialize you like in a crazy place. But then two, it's really the geometry of the model through the gradients of the loss or the gradients of the model with respect to parameters that tells you with respect to which Riemannian metric you're kind of doing gradient descent, so to speak. And it's really the combination of you start in a reasonable place and the Riemannian metric somehow has some implicit bias in it. And it tells you which way you're going to go to fit the data. So I somehow said it rather glibly before that neural networks approximate all functions. I basically believe that. And so the only difference between them is the way that parameterize those functions. You know, different kinds of architectures will prefer to fit data in different ways. And that's what's going to distinguish them. So that's kind of what I honestly mean by that remark. Is that reasonable? Is that good? Satisfactory? Okay, good. Okay, thank you. Okay, so let me tell you about at least one idea. I don't know how much time. I have plenty of time. Good. Okay, so here's key idea number one. So here's key idea. Okay, at least this is one of my favorite ideas. Okay, so in some ways I'm going to say this a bit historically how I approach these problems, but it doesn't matter. I think it's okay. So key idea number one is, so let's first imagine fixing the number of samples. Okay, it's very sad. Zohar's about to run out if there weren't so many people constraining him. But okay, it's okay. It's okay. We're going to come back, I promise. Okay, so let's fix the number of training data samples and ask, now I have this kind of more or less precise question. I want to understand the statistics of my neural network at initialization. I'm only going to evaluate it at a finite number of training data points, maybe a finite number of test data points. Okay, so what am I going to do? I'm going to study the regime where the hidden layer widths of the network are large. I'm going to think of them as proportional to a single large number n. This is like a typical way people increase number of parameters in practice. They make the model wider. That's not totally crazy. So n can be reasonably big. So here's kind of the TLDR of a lot of, okay, embarrassing in retrospect. Shouldn't have been that painful, but it was. Things I was thinking about and others were thinking about is that there's actually an emergent notion of effective depth of the network. Okay, so when I write L over N, I really mean the sum of the reciprocals, to be very precise, of the hidden layer widths. So in a way I'm about to explain, this plays the role of an effective depth. And I'll say maybe at/near initialization. Okay, so typically when people talk about the depth of a network, they say number of layers is the depth. That's kind of literally what people say. And I'm telling you that's wrong. Okay, what does it mean to be wrong? I'll tell you what I mean by it. But like, I don't think that's a useful way of talking about it. Okay, like a much better thermodynamic variable turns out to be L over N, as I'm about to try to convince you. Okay, so here's kind of the basic picture. All right, this is my favorite diagram of all time. If you've ever seen me give a talk, you probably saw this diagram. Okay, so I basically think of neural networks as having these two large parameters, at least in this kind of regime. There's the number of layers in your model, and there's the size of each layer. Those are my two summary parameters. And at least I think like as an intuitive thing, I think of L as a time variable. It's like, think of the neural network as a dynamical system. Time one evolution is go through one extra layer. That's not totally crazy. Okay, and in this dictionary, N is then the number of degrees of freedom in my model. Okay, but from this point of view, you see that there's going to be this titanic battle between N and L, right? Bigger systems take longer to come to equilibrium. And so N and L are somehow going to fight each other. Okay, so up here, when you fix the depth of the network and you let the width go to infinity, and I should flag with this particular normalization, okay, I'll say more about that offline if people are interested, then you get what's called the NTK regime, which maybe for this audience is better to call the free theory regime. Okay, so neural networks at initialization converge to the Gaussian processes. You just get the free theory, but that's just kind of the tip of the iceberg. In fact, maybe I should also call it the linear regime. because neural networks become linear models, it's as if they have depth 0. You see, a linear model would just be this, that the output is just W times X. Every linear model looks like that. And so indeed, that's what I'm about to tell you. That when you ask, how close are you? Okay, I have this model, and 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 you ask, which one of them is closer to being in this kind of NTK regime? The answer is, this one's the closest because it has the smallest effective depth. And this is kind of the depth 0 world. No depth, you look exactly like a linear model. And okay, let me finish drawing the picture and then say something more precise about it. But the point is this, the limits as n and L go to infinity don't commute, and you have to add a new variable to understand kind of what the phase diagram looks like. And this new variable is just this ratio of L over N. Okay, so you have this kind of new variable here, L over N, gamma, and gamma goes from 0 to infinity. And here neural networks basically become trainable, linear. And so it's a little sad, you want to be more trainable but less linear. And here neural networks in this opposite direction become less linear. I don't know what to say. And over here, they're simply untrainable. Untrainable. They're too unstable to tolerate gradient-based optimization. Okay, so there's some battle between N and L. And let me just be like epsilon more precise, because I'm going to come back to this in the next lecture when I actually do some derivations. I told you I would be mainly waving my hands today and making funny jokes, okay, at least potentially funny jokes. And I'll leave that adjudication to you. Okay, so what do I really mean? What does L over N actually control? Let me keep this. Okay, so L over N measures the following thing. So L over N measures in various senses how close you are to being a linear model. Okay, so here's sense number 1, which we'll come back to next time. So it measures how close to being a free theory at initialization. How close are your statistics to Gaussian? We've already seen a lot of talk of correlation functions. We'll see that L over N controls the size of the connected correlation function. Okay, but it goes beyond that. It measures how small is the Hessian of your model with respect to its parameters. Right? A linear model, by definition, is one where the Hessian is 0. I hope that's an uncontroversial statement. Okay, so you might ask, how big is the Hessian? Well, okay, you can calculate it. Okay, if you give yourself enough cups of coffee and motivation and things like that. And it turns out that it goes to 0 when N grows, but it actually becomes bigger and bigger with L. Okay, so if you want, you can kind of take these two things together and you can say larger depth amplifies the finite width corrections. It's like larger depth is a relevant perturbation. If you want to think about it, I think that's the right field theory language to use. Yeah.
Hessian for a linear model is XTX. I misunderstand.
Say again, please.
Hessian of a linear model is XTX.
No. That's not true. I'm not talking about the Hessian of the loss. I'm talking about the Hessian of the model. The model is linear in the parameters, and its Hessian is 0. But the loss is quadratic. Okay. So I'm not talking about the Hessian of the loss, only the Hessian of the model.
The Hessian of the output.
Yeah. So this is the Hessian of Z, not of the loss. Indeed. Right. Good. Very nice. Okay. What else do I get? So maybe let me report one more thing. So what's the right thing to say? Let me think about how I want to phrase this. Okay, maybe I say it this way. So maybe I say it as an upshot, okay, of like lots of people's work. Basically, as N goes to infinity, you get a kind of trivial / free theory. So you can do, and that's what I'll show you next time, 1 over N expansion for this theory. Okay, it's like, well, it's actually not that bad, although it was bad originally when I thought about it. Get a 1 over N expansion. You can get, in fact, layer-wise recursions for these perturbations. So it becomes kind of a perturbatively solvable 1 over N expansion where I say, The coefficients in the 1 over n expansion after L layers are explicitly write downable in terms of the coefficient in the 1 over n expansion in terms of L minus 1 layers. And then the initial condition is easy because the initial condition after 0 layers, if you want, is everything is Gaussian. So nothing stops you from doing all the calculations. Okay, so you can get this. I'll show you how to get that next time. And what you learn is that L is a relevant perturbation. And that's sort of, at least like in the way I think about it, I think like when you have a scaling limit of a model, you do perturbation theory. And you turn on all the other variables to see if, as they grow, you get further and further away from the model you were perturbing around. And that's kind of the point I'm trying to make. Here you have non-interacting free theories. But as soon as you turn on this L over n, you have more and more and more interactions in your theory. That's literally what happens. All the higher correlation functions are non-trivial at positive L over n. And like, oh, okay. So that's like, yeah, please.
Thank you, Boris. So yesterday, sort of Jim laid out for us quite clearly the emergence of the NTK without reference to a particular initialization distribution, just by like central limit arguments in function space. This perturbative regime that you were discussing, is it predicated on this particular initialization distribution, or can it still emerge? Like,
okay, so great. I should have been a bit more clear. So let me say, if by distribution you mean like, is it universal? Like if I replace the Gaussian by something else with the same moments, for sure you still get the NTK. I just talk about the Gaussian, it's easier to do calculations. But you in fact don't get the NTK regime if you let the width go to infinity. If you not only change the initialization, but you also change the way your optimizer works. I deleted the optimizer. But essentially in the final hidden layer, instead of a 1 over square root of n, you put a 1 over n. And then you have to take the learning rate and you have to make it scale with the width, linearly in the width of your model. It's a different kind of way of coupling all of your parameters, and you get a mean field, what's sometimes called rich regime. And like, that's related to Wasserstein gradient flows and interact. So it's like, yeah, it's a bit subtle, but you can get these totally different scalings that come out. But like maybe a different way of saying it is people thought hard about in this fixed depth limit, how do you escape this kind of slightly sad NTK regime? And the answer was, you do this mean field or kind of like, whatever you want to call it, parameterization. But I'm saying you could also go deeper. And it turns out they're actually the same. Like if you do the mean field parameterization of deep networks, that actually coincides with the NTK. So they're not so different in some ways of thinking about it. Yeah.
Before you erase that, which you're about to do, you talk about the correlation, measuring everything by higher order.
Yeah.
But then presumably there's some issue of radius and convergence, right? If you're doing this sort of expansion. And I'm wondering whether this limit helps you say anything about the radius of convergence.
So okay, that's totally reasonable. And the short answer is it's a bit of a disaster. What I would say is, okay, I'm putting my mathematician hat on to be completely precise. What I would say is the perturbation theory works perfectly fine, but things at order 1 over n will scale like L over n. And we'll have remainders like 1 over n squared. But those remainders scale like L over n squared. So actually like L over n is like a cutoff for your theory. If you want to do the perturbation theory, you really should think of L over n as being itself small, if you want the kind of like perturbative corrections to be the right ones. And what actually happened, instead of things being linear in L over n, like the kind of small L over n perturbation theory suggests, things are exponential in L over n. There are some exactly solvable models where you can get it. And so you're just really Taylor expanding some exponential. So it's actually more subtle. And no one fully knows in general. So it's definitely like a real question, and that's kind of what I think I should say about it. So let me erase this.
To understand your language, you're calling it effective depth because the linear model is literally a depth zero model of some other architecture associated with the first order data.
Yeah. So indeed, it's a bit of an artistic license, but at least for me, like, the hallmark of the NTK regime is that you're a Gaussian process at initialization and you can linearize and do your training. But like, that sounds like a linear model to me.
Yeah.
And so there's some precise like, okay, malleable calculus sense in which that's literally true, but like, it basically is saying that you just take your model and you Taylor expand it to first order and all the weights, and you can drop the higher order bits.
And so the weights are not just the output weights of the original model, it's all the weights.
All of them.
So it's depth zero in some different architecture, but it is literally depth zero.
So precise. So that's why I should be, yeah. So it's linear, but the feature map is not just mapped to the last layer.
Yeah.
There's some other feature map that comes from, okay, the NTK.
Features are d up by d theta and initialization of all of them.
Precisely. indeed. So still linear, but
Yes, sir.
So maybe following up on that, would you say, I can see that working for FCN and transformers because they're very homogeneous with depth. Would you see something like this for a CNN? For instance, if you cut it short, you're not pulling enough, and then you probably get stuck with an FCN too early or something like that.
yes, CNNs are subtle and kind of interesting. It depends how you take the infinite size limit. Like if you fix the number of channels, then actually you're really not approaching an NTK regime because like there's too many like correlated parameters. If by infinite size CNN, you mean you take the number of channels to infinity.
Yeah, but then there is a hierarchical depth is not homogeneous there.
Yeah, so I don't know how to work it out in that case. Like I'm sure that one can do it, and I think it'd be quite interesting to figure out because now indeed it's not only an N, there's also a kernel size, and then it's like I've always like secretly had the dream to do it, but you might be the hero we all need, you know what I mean? So okay, so let me erase this as well. Okay, so I have a couple more minutes, so let me say a little bit more. Very good. Somehow my selection too. All right. So I think I've said everything I should about that. Let me very briefly say, okay, this is to make Zohar happy because that's my main goal in life after all. Okay. So number two, okay, hopefully I can make him happy in 5 minutes and then say one more thing is so what if you have the number of samples and the width and the depth go to infinity together?
I mean, as long as you're looking at initialization and you're looking at these gradients, you don't even see the number of data points. So can you be more?
So indeed, I'm now thinking about doing Bayesian inference, for example, or taking a couple of steps of training and the number of data points I expose it to, it goes to infinity. So like, yeah, maybe to connect to the things that you do, like maybe think of L fixed, and I just want to take both of them large and study some kind of thing where in the action I feel both the kind of like likelihood and the prior in equal proportion. So here, like we understand much less. Like what I told you is that the limits as n and L go to infinity don't commute, and it's L over n that's important. What a lot of people's work, including Zohar's, tells you is that if L is fixed, then the limits as the number of samples and the width go to infinity don't like commute. And it's the ratio again that's important. That's like a number or different like refinements of the ratio if you have more kind of fine-grained controlled on the kind of way you generated your data. And it's not totally clear what happens when all of them go to infinity. And so I will hopefully have time to get back to this in the next lecture, but let me draw a picture just in case not. Like, so this is like, I tried to study this kind of thing together with a really amazing PhD student named Alexander Zlokapa. Okay, he's a PhD student at MIT. And so I'm just going to very briefly report to you how to refine this kind of phase diagram to also have the number of samples go to infinity. What we did is we studied Bayesian inference with these kind of deep, fully connected networks. And the picture I draw for you, we only fully proved everything in the case of deep linear networks. Okay, you take the nonlinearity, you just drop it. It's just the identity. Your whole output is just the product of matrices times the n. And you might say that's too trivial, but it was pretty hard for me. So maybe there's good room for you to do something exciting. Okay, so here's basically what we learned. There was a new thing that came up. It was the number of samples times depth over width, called lambda. And this is actually the thing that played the role of the effective depth after training. So what I mean is the phase diagram now kind of looked like this. You have to blow up this corner of the phase diagram when talking about what happens. So let me draw it and I'll try to say something sensible. A little hard to speak generally without doing computations, but I'm going to leave the computations for next time. Okay, so it turns out there are two phases for learning basically. There's the phase parameterized by this number of samples times depth over width, which I'm calling lambda. So here lambda is 0, here lambda is infinity. And then there's a second phase parameterized by L over n, which I called gamma before. Here gamma was 0, here gamma is infinity. And what happens is you are actually close to the NTK regime, the regime where you first send the depth and the width to infinity, and everything becomes a linear model, if lambda goes to 0. So this is kind of your new notion of effective depth. And without belaboring it too much, let me just say there are two phases of learning. There are weakly coupled kind of posteriors, and there are strongly coupled posteriors. And there's an interesting phase transition that happens over here. And so it's like, even for these deep linear networks, there are actually two notions of effective depth So that's like effective depth after learning, and this is like, you know, effective depth of the prior. And let me say, I spoke with Zohar and with his then PhD student Inbar about this a while ago. And like this thing kind of comes up in their analysis too. But like lots of people, like the novelty of what we did is we took the depth to infinity together with everything else. But if you first fix the depth, you take the width and the number of samples to infinity, you do something about studying learning, say by Bayesian inference. Then you take the depth to infinity. You still again see this kind of combination of factors coming up. So I'm just saying, like, this is meant to land the airplane a little bit. This is a surprisingly complicated, for me, phase diagram for learning linear networks. Linear networks, geez, they're always linear in the input. They're just not linear in the parameters. And it's like, for me, I had no idea that it would be this combination of the variables that came up, or these two combinations to determine the nature of what you learn. So it's like, I felt like that was a good kind of thing to understand. This almost surely is the thing for SGT2 for what it's worth. I just haven't finished proving it.
Yeah, dimension. So if I want to think about that this diagram confusing me a bit, first I increase n until I get the first lambda to infinity, and then at some point it sort of saturates and I start ignoring n and think about L over L.
Yeah, so okay, maybe I should be precise. So here, input dimension, number of samples go to infinity at a fixed ratio. This converges to some alpha less than 1. It's the linear model, so like I kind of need to have, otherwise I only have 1 point. Okay, so that's how it is. And then simultaneously all the NLs go to infinity and L goes to, so that's kind of the thing we literally do. Yeah. So we're taking the limit where they have a sequence of data generating processes, one in every dimension, and like everything is growing. But
in this phase, this new phase that you're describing, the lower wing there,
yeah,
you don't depend on the data.
So all the posteriors depend on the data in a completely explicit way, which we can write down. Yeah. So they actually don't. Well, they depend on small n only through this thing. But then the limiting posterior depends on the value of lambda and certain coarse statistics of your data. Like they depend on alpha 0 and they depend on the norm of the minimal norm interpolant, and that they kind of like.
But on this other side, you don't depend on the data on the side of the data set anymore.
Yeah, so correct. The phase transition you have is your posterior freezes and you get a universal posterior here, regardless of the value of little n that you kind of chose. But what changes here is the evidence. Your partition function actually still changes. So there's still a kind of best gamma to choose that depends on the data, but you don't see it from the point of view of the posterior. That's kind of like what we're talking about. Okay, so let's see. I have a couple of minutes left. Let me just say, this is just meant to be some sketches of like, I think these are cool things. I like phase diagrams. You like phase diagrams. Okay, maybe we can all get along, kind of thing. Okay, but let me end, if you guys don't mind too much, on one like slightly more technical idea, which I hope you will ruminate on, or at least will allow me to jog your memory tomorrow if you want more, of all this. And it's a very simple observation, but it's kind of key to the whole study of everything. So when you take seriously the question of, can I describe the distribution of the network and maybe its derivatives at initialization, you quickly run into the question of why should it be possible? Sounds complicated, looks pretty complicated to me, but it's not. Okay, the reason it's not is like always, at least this is how I was taught physics, there's a big symmetry group. Okay, so maybe this is kind of key idea number 3. You have a natural symmetry group. And what's the symmetry group? Well, the symmetry group is you have a copy of the symmetric group in every hidden layer. It doesn't matter how you number the neurons. Okay, so your symmetry group, formally speaking, is like this. You have the symmetry group on N1 characters, product symmetry group on NL characters. Okay, statisticians would say the neurons are exchangeable. I don't know what physicists say. I say it has a symmetry group. So what this basically means is that all aspects of training, doesn't matter if it's at initialization or not, depend only on averages over neurons. Okay, this is a non-asymptotic statement. So I'm going to introduce my notation for an average. I call it O for observable. Call these collective observables, not that it matters. Okay, so it's the average over the neurons in a layer of a fixed function applied to what you see in that layer. J alpha, okay, maybe alpha lies in A. Okay, I've lied to you very slightly, but I'm not going to tell you how I lied to you so that I can make the point I'm about to make, but come ask me. But this is basically the truth. This is how all the DMFT kind of papers are written. This is why you know they were going to succeed to begin with. They find an exact way to rewrite the dynamics, which were in terms of the weights, only in terms of averages of a finite number of functions over the neurons in each layer. It's like a huge simplification. And you can see that these are the kind of things that are going to be our order parameters. Obviously, these are going to like somehow self-average if you take n to infinity before everything else. That's how you kind of get the NTK regime. Okay, so let me do an example for you because it's going to come up next time, but I want to kind of land the airplane. So remember that, if I look at a particular pre-activation in layer L+1, I'm just writing out the formula for it because, well, I don't know, it's good to look at. Okay, so it looks like this, Ij sigma CLJ alpha. That's what it is. So why is this distribution complicated? Well, it has a complicated bit and it has an easy bit. The easy bit is the Gaussian weights, right? These are IID Gaussian weights. When you sum up a bunch of Gaussians, you get a Gaussian. Okay, that's easy. But the difficult part is that they share this previous layer's activations. That's kind of what correlates. Okay, so we see the following statement. Okay, so if I tell you that I condition first on what happened in the previous layer, I give you all the pre-activations. Then what happens? Well, these things, these ZL+1 I alphas, as a function of I, this is all the neurons you have in layer L+1, are just independent, centered Gaussians, right? Because once you condition on what happened in the previous layer, it's like I gave you these sigmas. And then every neuron has its own weights. The Wijs are independent. So more precisely, okay, if you allow me to be a bit of a probabilist, I'll write covariance for the second connected correlation function, right? So the covariance between what happens at neuron I at input alpha and neuron J at input beta, given what happened at the previous layer, is just delta Ij times, okay, how do you compute the correlation between dot products with a Gaussian? It's just the dot product to the two vectors. Okay, so I take 1 over square root of n times the vector of activations I had at input alpha, and I take a dot product with the vector of activations I had at input beta. Sorry, and the variances are CW in my normalization. J goes from 1 up to NL, sigma ZL J alpha, sigma CL J beta. And hey, what do you know? That's a collective observable. Okay, I'm just saying, if you want to put it this way, that at every layer, actually what I see is a free field, but the trick is I have a fluctuating and shared 2-point function. That's literally the structure of these field theories. Okay, so maybe I write that down and then I stop, because I should stop in about 17 seconds. Or maybe I started 12 seconds late, so maybe I get 29 seconds or something like that. Okay, so this is really going to be our starting point next time. So the point is that ZL, I guess I wrote L+1, I alpha, are free theories, but with a fluctuating, at least it fluctuates at finite size, fluctuating metric or 2-point function, and I'm just going to give this thing a name. Okay, this is going to be sigma L alpha beta, actually L+1 since they were okay, sigma L+1 alpha beta.
So Boris, it's the adaptive kernel in a way, right?
Say again, please.
The adaptive kernel, basically.
Yeah, precisely. That's all I'm saying. Yeah. So right. So I could have used those terms too. It's like an adaptive kernel. It's like at every field, at every layer, you get this fresh randomness which makes you free, but not exactly. Like every neuron in the next layer shares the same kind of pre-activations in the previous layer. So they're all correlated and they're all not free. Like a free field with a fluctuating 2-point function is not free. Or maybe it's almost free.
Fluctuating layer by layer.
Say again?
Fluctuating layer by layer.
So sorry, what I mean is like this is a random object that depends on the weights up to that layer.
Yeah.
And so like so in every layer it's random. Except in the first layer.
But it depends on what happened.
Yeah, right. So they're correlated random 2-point functions in each layer. But this is a huge simplification. This is related to the kind of things that Jim has written a couple of papers about, which I thought were really nice. Like I think everyone kind of starts from this observation. This is like the structure. I think you call it the structure of neural network field theories. Maybe that's what you call it. Am I getting that wrong? But I'm just saying this is a huge structural reduction to what like a field theory looks like, right? Like everything's for you with a random 2-point function. It's like let's go. Everything's gonna be Gaussian. Right? That's how I think about it. Okay. So let me stop. Next time, what I'm gonna do is I'm gonna start with this observation, and I'm actually gonna tell you how to compute recursively all the connected correlation functions of this field at layer L+1 in terms of the field at layer L. We'll solve some of these recursions. We'll see L over N appear. Like next time will be more about, doing real things rather than talking. But I hope this gives you a sense of where I'm going.
When the protein is found in novel, is from stranger in a strange land.
Really?
Yes.
Okay. I mean, okay. I can easily be wrong about that. I was kind of certain, but not that certain. Not as certain as I am about this thing.
So Boris, in terms of general parameters, I might have thought that there would be one more. It would be about the dimensionality of the data relative to the dimensionality of the embedding space.
So that actually does appear if you think about it. You see in the first layer, you have a free theory, but your kernel, like sigma 1 alpha beta, is actually this dot product kernel, x alpha dot x beta. And so you see here you have the ratio between the ambient dimension and something about the typical correlations between the x's. And so that actually gets captured in this first kernel.
But it doesn't, in the phase diagram sense, it's not something that simply emerges as one more parameter to add.
So here I had to basically fix that parameter. So it does emerge, but I just carry it along. You have to know something about like how many directions you observe in your training data set. And then there's another statistic, which is basically related to the spectrum of the sample covariance matrix, which tells you about kind of how effectively high or low dimensional the data points you observe them. I just didn't specify that, but you're totally right. There is a full data dependence or some vestige of the data dependence in all of these lists there.